Hello, everybody. Mr. Rubo here, and today I'm gonna have you guys do some always, sometimes, never questions, and then on 7-3, and then some true and false on 7-4, and then I want you guys to try some practice on 5, 6, and 7. Um, for the always, sometimes, never, and this true and false, though, I will go over it, just because sometimes the explanations are a little tough. So I want you to try them out first on your own. So that way, you kind of think about it a little bit and then come back into the video to see if you got it right. And if you didn't, then we'll go over the answer. And if you did get it right, then great job. No need for the explanation if you understood it, but maybe if you even got it right, maybe if you didn't know the explanation exactly, uh, it might be something that you take a look at. All right. All right. So, like I said, go ahead, pause the video, go on, and take some time to try this out. And yeah. All right. So hopefully you tried out at least the sometimes, always, never. So here, if a hexagon is equilateral, then it is regular. So unfortunately, this one gets students all the time. My stylus does not want to write. This guy. Oh, no. Um, there we go. Is sometimes true. So the reason why this is always kind of a lot of times students put always is because with triangles, this is true. It's always true, I should say. With anything with more sides than a triangle, it's sometimes true. So equilateral with all the same sides. Now it is possible to draw this. Obviously, I'm going to be drawing it. So that 1, 2, 3, 4, 5. I could draw a figure. Usually, the ones that kind of mess things up are these concave figures. Again, I probably could have drawn this better, but it could be equilateral, but the angles aren't the same, which means it is not regular. It also works the other way. If it's equal angular, it's not always equilateral. That's only true with triangles, and that's kind of leads us right into number 2. An equal angular triangle is equilateral. That is always. And like I said, that's the special case. Triangles, equal angular, equilateral are the same shape, but everything else is not. Now here, an equilateral quadrilateral is a square. Well, we just spent a lot of time with quadrilaterals. Equilateral, meaning all the sides are the same. Well, this is sometimes true. Because a square is definitely an equilateral quadrilateral, but so is a rhombus. And a rhombus is not always a square. So I can draw an equilateral quadrilateral. That's not a square. All right, the diagonals of a regular polygon are congruent. So unfortunately for this one, this is sometimes as well. And this kind of, again, goes back to quadrilaterals where we spend a lot of time, right? If we had a square, its diagonals are congruent. But let's just go... what shape do I want to go? Let's go this guy. So, pretend that's a straight line. Oh, man, I can't draw my hexagon very well. Here we go. So, if I draw even just the diagonals from one vertex, I have this guy. That did not change colors here. And I have this guy. Those would definitely be congruent. But if I draw the one that goes straight, like vertical, it's definitely longer than those two. So right there, you can see, even in the case of a hexagon, it is sometimes true, but like we know it's true for quadrilaterals that are regular, so that's why it's sometimes. 5, a polygon has to be regular in order to form isosceles triangles with 2 of its diagonals. So this guy is, trying to think through all of your options. Again, this is another one of those. This is sometimes true. Let's go pentagon. So if I draw where it's not regular, so let's say, we can kind of clearly see that it's not the same. But I can draw these 2 diagonals, and for the sake of argument, I could draw it where those are the same, even though that the other lengths are not, so it's not a regular shape. But it definitely works if it is regular. Okay. The perpendicular bisectors of the sides of regular polygons bisect the angle. So if we look here, perpendicular bisectors of the sides of a regular polygon bisect an angle. Well, we know this to be true for triangles, right? Regular triangles, also known as equilateral. It works, but let's go square. So again, very familiar shape. Perpendicular bisector means I'm going through the middle and I'm perpendicular. That does not hit a vertex, does not bisect an angle. So this is sometimes. An exterior angle of a polygon is supplementary to a corresponding interior angle. Well, that one hopefully you tried and gave always, because that is like literally the definition of an exterior angle. 8, if the length of the sides of a polygon is doubled, then the measure of the interior angle is also doubled. Well, let's go ahead and let's keep it simple. Let's draw a square. Pretend that's a square, everybody. Square. So if it's 1, 1, 1, and 1, and I double it to 2, 2, 2, and 2, it's still a square, which means it's still got right angles, which means that this does not happen. And you can try all you want, but if you are just taking the lengths of the polygon, of any polygon, and doubling them, you're making a dilation, thinking back to transformations way back at the beginning of the year. And dilations do not change the shape. In other words, they don't change the angles. Those stay the same. So this is actually never true. And then the last one on the always, sometimes, never, if the number of sides is double, the sum of the interior angles is also doubled. So let's just use our formula. So we know that, if the number of sides is doubled, so it becomes 2n, we just use our formula, so 2n minus 2 times 180. We want to see, is that the same as doing n minus 2 times 180 doubled? Like, that's what we're looking, is if you did just the normal angle and you double it, is it the same as if you put 2n in to the formula? So if you start solving this and doing some math, you end up and actually, really nice thing is, think of this like an equation. We don't know whether it's equal or not, but they're both being multiplied by 180, so we can kind of just cancel that out, and you get 2n minus 4, 2n minus 2, and it ends up, again, same thing on both sides, if you will. We would get negative 2 is equal to negative 4, but that's definitely not true. So this is never going to happen. You can try all you want. You can do it with some examples, right? You can try, thinking about a triangle, plugging it in, and then trying it with a hexagon, and you'll see that you definitely do not get the same. No, I'm sorry, you don't get the double of the interior. Okay, so there you go, and hopefully those explanations make sense. And now go ahead and do the same thing with these. What, 1, 2, 3, 4, 5 true and false. Pause the video, come back, and check it out with the explanation. And then, yeah. All right, so number 10, the exterior angles of a polygon is constant. Constant meaning the same. This is not true. Ooh, sorry about that. Hit my arm on the thing. Sorry, it is sometimes true. And you might be like, oh yeah, like the first thing you should think of is any regular. So if it's regular, it works. But it does not say regular here. So this is false because it is not always true. Okay, so that's the one thing. Remember, with true and false, you're looking for a statement that is always true. So 11. Did I count wrong before? Yeah, I did. There's only 4 questions here. There can exist a quadrilateral with 3 obtuse angles. So if you draw it, like this one is just saying there can exist. So you don't have to think about all quadrilaterals. You just have to come up with one where, and you can even try drawing it. We have an obtuse angle that's then connected to another obtuse angle. Ooh, that doesn't look like. Sorry, my. Ooh, yeah, I can't draw right now. Sorry about that. So, obtuse angle, and it does actually work. It does exist, and it is usually a kite. Actually, is one example where that can happen. There can exist a pentagon with 4 of its right 4 angles of 90 degrees. So 4 right angles. So this one, let's go ahead and think about what's the total amount in a pentagon. So let's do 5 minus 2 times 180. Okay, just to see what that equals. And that is 540. And if 4 of your angles are 90 degrees, well, that means I'm subtracting 360. My stylus did not want to make a 3 there, which means you are left with 180 degrees for your last angle, which means that's not possible. You can't have a straight angle as one of your vertices. So this is false. This would just be a never statement if it was always sometimes never. All right, so let's go ahead and try this one out. So there can exist a quadrilateral with angles measuring 40, 60, and 70. So this case, we already know, well, we might remember, hopefully, 360 degrees is in a quadrilateral. Let's just subtract all of these. Oops, not just those 2, all of them. Okay, and when you do that, that's 170. You subtract it, and then you end up with what? 290? 290. I can't do math today. Yeah, no. So 190. Pretend I can do my math. Right? So now I'm double checking everything because second guessing myself. That's 300 minus another 40 is 260. 260 minus 70. Yeah. Okay. Okay. And so you may be like, well, you just said you can't have a straight angle, and that is true. You can't have a straight angle to make a side, but you can actually have angles over 180 because if you draw this out, this guy is just a concave. It's a little over. So that's 190 degrees. And the other ones work. So this is a true statement because it can exist. Okay, so 180 is bad, but pretty much anything less than 360 is okay, right? Anything less than 360 that is not 180, you can draw it being concave. Okay. All right. So for the rest of the time, go ahead and try out 5 and 6 and page 7 as well. Those ones, the key is on Canvas, so just check there. But yeah, thanks for watching and have